Today, I will present my final project, which is in the topic of medical imaging. First is the project overview. The dataset we have is 21 pairs of pictures. Each pair consists of a slide image of cells and a corresponding tumor mask. The starter code was given with instructions on how to read slides using OpenSlide. The goal of this project is to predict the tumor mask for a new slide image using multiple zoom levels with high magnificence images. First step is to do the pre-processing. We have the 21 pairs. I randomly choose 3 pairs to be the test set, which have the indices listed here, 3 pairs of the validation set, and all others are the train set. For the train set and validation set, I use the original images in level 2 and level 3 to create the input for my model. I cropped one large image into multiple small images of size 128, 128. The general idea is shown in the image with the grid, which is here. I try to crop this large image into multiple small images with the length to be 21, 28. I ignore the remainder area, which is here, because when I crop the image, the remainder area will be at the edge of the large image, which we actually do not need to predict, and the remainder will also be small enough to ignore. In order to not miss the information at the grid line, which is the edge of the small images, such as those regions, I changed the thread to be 120, which is shown by the Y square. So for example, if the first image I crop is here, then the next image I crop will be here. In this way, none of the important points will be only at the edge of the new images. As given in the starter code, I used the tissue percentage to be 0.2. In order not to get too many empty images, I set the threshold to be 0.2, which means only when I have more than 20% of the images be tissues, I will consider these images for future use. In order to have a more balanced data, because most of the images have too large proportions of the normal area than the infected area, I set the bound of number of normal images to be no more than 5 times the number of infected images. So for example, it means if I have 10 images for the infected tumors, then if I have 50 images for the normal tumors, I will no longer save the normal images to my folder. To avoid of selecting the continuous areas, such as the first 5 images in the first row, for example, in order not to only select it row by row, I created a list of all possible indices for the left out points, then randomly pop the index from the list, then crop the images, which means I created a list of those index, which is the left out point of the new images, and then pop from this list. Finally, I got a train set of 20,000 images and a validation set of 9,800 images. Below is an example. The first image is the slide, then tumor mask, then a combination of the two. I created the generator by myself, which returns 32 pairs of corresponding images in level 2 and level 3, and the output of corresponding mask in level 2. 32 here is the batch size. The 2 input images have the same center, so the image of level 3 should be able to show a larger region than level 2. In this example, the first image has the shape 128, 128.3 because it is in the RGB version in level 2. And it is a more clear version of the white square in the second images, which is this area. The second picture has the same shape but with a lower resolution of a larger region. The third image is the corresponding mask of the first image, which is also in level 2. I selected in this way because I think instead of showing a higher resolution of the same area, showing its surrounding area will have more geometric meaning. Based on the UNet with small changes in the model. For the encoder, I built some convolutional and pooling layers to process the 2 inputs individually, then concatenate the 2 small matrices like the bottom area at here. For the encoder, I concatenate from the corresponding level, then did the transpose So it's like I concatenate this area with this thing together and then did the transpose convolutional layer to expand the matrix size and decrease the matrix thickness. Because we have highly unbalanced proportion of being 0 and 1 in the mask images, most points are 0, so there will be more points that has true label 0 being predicted as 1, and only a small proportion of points are 1, so there will be less points which has a true label of 1 but being predicted as 0. I use the sigmoid focal cross entropy for the loss function to give a lower weight where true value is 0 and predicted to be 1, and give a higher weight to the points where true value is 1 and predicted to be 0, because we want to detect more points. I trained the model for 20 epochs and saved the weights in each step using the checkpoints. The validation accuracy reached 0.98 after 20 epochs, but keep in mind that the high accuracy does not mean the model is very good because we are having too many points being 0. Even using a model that can only output 0 will give a high accuracy. So we need to see the prediction mask. Since the prediction should have the same size with level 2 input, in order not to exceed the RAM, I created the prediction in level 5 by combining 8 by 8 pixels into 1 pixel. The color of the new pixel is mean of 64 pixels. If the mean is greater or equal to 0.5, assign the value to be 1, and otherwise assign 0. The input for prediction was manually batched and cropped. I did not use the previous data generator because I need the sequence of the new images to concatenate to a full image. Here is the prediction result. For index 75, we can see that the shape of the infecting area in prediction has similar shape with the true mask, which is like in this area and this area, but with much smaller area size. It is the same for index 78. The prediction has smaller area. For index 120, it looks better, but still some points inside the yellow area, like here, was predicted to be normal, but they're infected. In order to evaluate how the model performed, I use first is the proportion of infected area that are being detected. We can see that even though the model performs better in image 75, the detection proportion is still very low for test sets. Next metric is type 1 error, which has the true label 0 but was predicted to be 1. I divided the number of type 1 error pixels by the total number of pixels I have to get the proportion, which is listed here. The last metric is the type 2 error proportion, which has the true label of 1 but was predicted to be 0. We mentioned before that since there are much more 0 points, so type 1 error should have a larger proportion than type 2 error, but it is not the case in the result. The reason might be that the focal cross entropy might give a too high weight to type 1, so we are predicting more points to be 0. It is obvious that image 75 has a error than image 78 and image 110. It is because more percentage of the infected points were detected in image 75, and it matches the result of the proportion of being detected. Next is the code walkthrough. So this file, I used this file to crop the images, and I did that locally on my computer. I will need to change the target to be validation to crop the validation set. So first I have the slide path and tumor path. Then here I calculate the number of images I need to crop and created a list of all indices. Then for each time I pop a pair from the list and crop the first image in level 2. Only when the percent tissue is larger than 20%, I process to the similar area in level 3 and the corresponding mask. Actually, I did crop the mask for level 3, but I end up did not use that for the output. Then I did some post-processing and then saved the image. Next is the build model notebook. So first, I created the train and validation paths. Then I calculate how many dataset I have in each set and give an example. Then I created the generator for the image in level 2, image in level 3, and mask in level 1 in level 2. Then I created the train dataset and validation dataset. I give an example in the train dataset by the generator to see if the shape is correct, and I also plot an example. Then I build the unit by myself. Until here is the left side of the unit, and the merge is the bottom side of the unit, and the decoder is the right side of the unit, which we can see that I concatenate the previous input and the output I got from the convolutional to the transpose, and then did the transpose convolution again. Here I use the sigmoid focal cross entropy as the loss function. Here is a plot of my model. Because it takes too long time to train the model, so I use the checkpoints to save the weight for each epoch. And here is a summary of the model. I trained 5 epochs each time, and then I did that for 4 times. So I trained the model for 20 epochs. And I saved the weight for the model so that I can use the model by loading the weight each time. I do not need to train it. Then I install the OpenSlide again, and I wrote the make prediction function by myself. The compressed prediction is the part I mentioned before that I compressed 8 times 8 pixel into a new pixel to decrease the prediction size to display it. I also wrote the find error function to give the proportion of being detected and type 1 and type 2 error. Here is the 3 examples in the test set. I created the table by myself. That's it for my presentation. Thank you for listening.